One of the best ways to learn about software engineering, embedded software, and firmware development is to not just write code, but to also read code. Now, I get the opportunity to write tens of thousands of lines of code every year and perform dozens of code and design reviews with customers. And I thought it would be kind of interesting to sit down and just do a code review on a real simple application, the Zephyr sample Blinky application, and let you kind of see the way that I think through code reviews, which might help you as you start to pick through your own code to see maybe what changes you'd want to make or to identify just the thought processes of how we review code. Again, I think this is one of the best ways to actually learn about developing robust software. And so let's dive in and take a look at a real simple application. So this Zephyr Blinky application is designed to do nothing more than blink an LED. And we can see here just from the code immediately on my screen here that it should blink an LED about once every second. So we can see first off the bat here that this code is nicely documented. We've got some documentation talking about our tick rate, that we're accessing LED 0 from an alias on the device tree. We can see here about build errors if we get a build error that this thing doesn't exist. So there is a little bit of documentation at least up front. As we start to look through the rest of this code, though, we can obviously see the green kind of goes away, and we don't necessarily see a lot of comments as to what's going on here. Now, that may not be a big deal. Just because there aren't comments there doesn't mean that the code is bad per se. Hopefully the code is actually really clean and it's very easy for us to understand what is happening in the software, right? But when we look at this, even at the very top piece here, I already start to see things that if I were performing a code review, I would really start to nitpick and make some adjustments to the way that this code is written, just even before we get to the main function. So as I look at this, one of the first things that catches my eye is the sleep time millisecond macro. It's specifying that 1,000 milliseconds is equal to a second. Okay, great. We got some documentation there. But if you're working in C, you know that macros themselves, especially if you have any macro expansions, that can result in some unexpected behavior, unexpected conversions, and some really strange things happening. On top of that, if I look at this 1,000, okay, it's just a value of 1,000. Is that okay? Should it be is it going to be treated as a signed integer, an unsigned integer? Does it need to have a long type? There's nothing really specified there that lets me understand what the intent of that 1,000 or what this macro is going to be used for. And so if I were to actually look at this in a code review, one of the first things I'd say is that, good practice for a macro, we should at least have some parentheses around this thing just to make it safe to be, in case it's used in some unexpected way. On top of that, I might even say, I want to throw a U in here to specify and make it a lot more clear and verbose that this is going to be treated like an unsigned integer later on in the application. Okay. Now, that right there is just kind of some general C best practices. On top of that, since I am working within the Zephyr environment, this sleep time milliseconds macro, it's obviously being used somewhere to manage the time of a task. And so if I scroll through here and look to see where it's being used, I find here at the bottom of the main thread here that it's being used as part of K sleep is essentially where I'm using it here. I'm going to specify the number of milliseconds that I want my thread to pause before we go back and repeat whatever it is that we're planning on doing here, which again, it's a Blinky application, so we're going to be blinking an LED. Now, because I'm working within Zephyr, this is perfectly acceptable. The compiler, the Zephyr system itself will be very happy with me doing that. But on top of this, there's actually some additional changes that I could make here to make this a lot more explicit as to what I'm using this for. Instead of making this a macro just keeping parentheses like that, I can actually use another. Whoops! If I can type here, I can actually use K milliseconds here to specify that hey, this is actually being specifically used with the K sleep function, and this is kind of being a lot more verbose, showing that yes, this is going to be used to manage time. I'm not going to be using it as part of any other functions. All right, and so this in and of itself will help us to specify and be a little bit clearer. Now, for a Blinky application, does this really make any difference? No, it doesn't. All it is doing is cleaning up and making things a little bit clearer to anyone who comes back later and reviews the code to make sure that they have a clean understanding of what the application or what the intent of this code actually is. And to be completely honest, that's where bugs come from, is when people aren't clear with the way that they're writing code. It's very easy to have misunderstandings, to extrapolate or change the code in a way that was not the original intent of the coder or the developer. And then we end up with a bug injection that no one really notices. And then later on down the road, we have technical debt and bugs and unhappy customers, that we have to deal with. Okay. Ultimately, would we see a huge change with this little change? Probably not. But again, a couple of little best practices there for those of you who are working with C and starting to work with Zephyr. Now, typically when we review code like this, we go line by line. And so we can see here there's another macro for the LED node, LED0 node. This is just pulling the alias for LED0 so that we can actually set up the device tree. We can get access to the references for this particular LED specifier in the device tree, which will, at the end of the day, just allow us to toggle a GPIO pin to control the LED. Okay, but looking through this, we can see there's some nice documentation. A nice thing here, we're seeing that this GPIO, the LED, the spec here which is a structure that manages the LED. We can see here that some good practices are being followed here. First, this is declared as constant. So that means once we specify LED, we can't go in and change the values that the device tree provides back to us. All right, so that's good. On top of that, we're declaring this as static, which means that we're limiting the scope of the LED variable here. And so that's good. We're limiting the scope. These are a couple best practices. We're declaring things constant where we can, and again, limiting scope. Okay, perfect. So let's continue to look through the code here. So this doesn't take all day for a simple Blinky. We can see here that we're then moving into the main thread. Now Zephyr, this particular main thread is it's a thread that's going to run automatically as part of our application. There's a couple different threads that show up. There's a main thread. There is also an idle thread. And then, of course, you can add your own threads to the application as well. But for this simple Blinky, we just have this one thread to worry about. Now, when I start to look through here, immediately to look at what this is doing, I can see that we have some initialization code here that's going to initialize further the LED for use. We can see here that we're checking to make sure that it's ready. We're actually configuring the GPIO pin. And so for a simple application, this is fine. I probably, in any real embedded application, would pull any initialization code out into its own separate functions. That way, the body of the thread is actually real simple and straightforward and reads very easily just by reading the function names. Okay, so I would see something like, LED init. And that would make it clear to me that when LED init runs, that it's going through and it's making sure that the device tree is ready, that the pin was configured, and probably sets it even to a default state. All right. So we can see here that by default, there isn't anything here that looks like it is setting a default state for the I/O pin. It's just coming in with whatever the state from the GPIO or from the device tree was actually set to. All right. Again, for a simple Blinky, who cares? But if you're writing production code, all these little things really help make your code a lot cleaner. And it can also ensure, again, that there is no misunderstanding as to what's happening in this function. Now, for our purposes, I'm just going to keep things simple. I'm going to keep the initialization in the body of the main here, rather than pulling out a separate function. But you can imagine all of this code being thrown into a nice LED init function would make the main thread look a lot cleaner. So one of the first things that actually catches my eyes, this init return variable. By default here, what's happening? Well, the compiler is going to initialize it, but it's going to initialize it to what? Maybe 0, or maybe some random value that's stored in the memory location. So right off the bat here, kind of a best practice is at least initialize this thing to something. And you can see here the recommendation is that, hey, you know what? We should define this as 0. Now, I think that's actually a really good recommendation. Although maybe I want to define something else, like, hey, maybe I want to come up here and say, let's define a new value like EOK, and we're going to specify that this is actually 0. Okay. And then maybe what I'll do is initialize this to EOK right off the bat here. Okay. So That's one example. We should make sure that any variables we create, even if they're just local variables, that we define and provide a default value for them. Okay. We can see that we then have an LED state that we're defining to be equal to true. That is certainly, I think, a good way for us to initialize the LED state. So LED state could be either on, it could be off. In this case, we're using a Boolean to define that state as true or false. But here's another bone that I have to pick. What exactly does that mean? The LED state is true. Does that mean that the LED is on? Does that mean that the LED is off? Right? That's not very clear as to what the LED state is actually specifying for us. So a better way to do this would actually be to create a typedef enum, and as part of that typedef enum, specify states like off and on. All right? Maybe the state of off actually specifies that the LED is a state of 0 numerically, and a 1 is that the LED is on. Okay, and so that is, I think, a real simple change that we could make here. And so again, maybe what I'll do here early on here at the top here, and I'm not going to include some comments. That would be something that would be nice to do. So what we'll do is we'll typedef, we'll create an enum. We'll just take the example that they're putting here, but what we'll do is we'll define an LED state type. And then in this particular case, we're going to have LED off. And we'll do LED on. And then there's certainly some arguments as to whether you go further and say LED maximum or something like that, right? To specify that this is the end of the actual enumerization, okay? You could go either way. It's kind of personal preference and coding style at that point. But then at this point, the simple bool here, we can now replace this with LED state type, and we can specify that the default should be LED off. All right. And now when I read this entry, I can see that I default to say that the return value is EOK, and then I'm defining an LED state variable, and that LED state is defaulted to an off state. All right. So that right there makes it a lot cleaner, a lot clearer as to what exactly my LED state equals true, what it actually means. Okay. Sure, we could extrapolate and assume that an LED state of true means that it's on. But again, there's no comments. There's nothing that's really specifying what that is. And so making the code cleaner and clearer is important. It's all about clarity. Okay. All right. So some real minor adjustments there just right off the bat. Let's take a look at the rest of the initialization here. We can see here that we're saying, hey, if the GPIO is ready, it is pulling the device tree. So we're checking the device tree and seeing, hey, is this actually valid? Is it specified? If not, then we're going to return true or return 0. All right. So we're going to exit the thread, not even go further. Now, there's a problem with this. Okay. And it's not just the problem of, there's best practices like from Israel that says any thread or any function should only have one exit path, which basically means there should only be a single return statement. So that's kind of a best practice. You can have, wars about syntax and stuff like that as to whether that's something that we should really care about. But what we're seeing here is that we're returning 0 in different situations where we actually have errors. And typically returning 0 means, hey, everything is okay. We're good to go. Except in this case, we're not good to go. We're actually going to exit this thread and report that everything is good when there's actually a device tree error. So right off the bat here, again, this is kind of making me say, this really probably isn't the best way for us to go through this and go through and initialize this LED. Because if we fail, we're going to return that everything is hunky-dory and perfectly good to go. So what are some options here that we can do? Well, first of all, we should return an error code that actually lets us know that there's a problem with the device tree. That way, if we ever exit this thread, we can actually check what the return value was further up in the software stack and get some useful information about what actually happened. Okay. Secondly, I can see here that I have multiple functions here that I'm setting and checking return values for, and I am, again, returning that there's, that things didn't go the way I expected. And when I see stuff like this, I see multiple returns. I start to see this if ret multiple times. This by itself makes me think, you know what? we might want to refactor this and make this code a lot cleaner. Okay, the way that this is written, excuse me, it's very functional, as in functional programming. It's very sequential in the way that we're thinking about this. Is the GPIO ready? Yes. Okay, now then check. Let's configure the pin. Was that successful? And so we have these this very sequential process where we're actually duplicating code. And if something does go wrong, we're not even returning a value that makes a lot of sense for someone to be able to go in and debug and understand what's happening here. So let's do a couple of things here right off the bat. Let's start by saying if the GPIO is ready, if this is actually true, okay, and you can see here that, don't always trust what AI is trying to tell you to do, okay? Copilot's yelling and saying, yes, let's make that a not. Let's not do that, okay? What we're actually going to do is say, if we're successful here, then we'll continue on, and we'll get, we'll let the return value actually return a value for us, okay? From here, there's an option here, right? That we're basically saying, hey, GPIO is ready, but and it was successful, so try the next thing. Hopefully that return value then actually returns successful. We had no problems with the device tree and the way that the pins are configured. Okay, but maybe there is a problem. If there is a problem, whoops, I can't type today. We want to return some type of error, right? And you can see here that the AI in this particular case actually has a really good recommendation. It's suggesting that we return an error code that there is no device. Okay. Now, if the device is not ready, it means that the device tree is probably messed up. There is no device maybe listed there. There could be other errors, but I think in general, this might be a good way to go. Okay. And everyone might have their own opinions on whether, how they might clean this up. But for us, a negative value with enodev will return a negative value saying, hey, you know what? There was a problem. Okay. And so we don't necessarily want to continue on and, we want to exit just like the original application was going to exit. Now, looking at the way that this code runs, you might be saying, well, Jacob, you just removed the ability for us to exit here and return and let the higher level application know that there was actually a problem. And you're right. And so instead, what we need to do is actually make sure that we return a value here, or we check here before we toggle the LED. If there's an error here, we don't want to go into this while loop. And so what we should do is say while the return value is greater than or equal to, and I'm not going to say that, I'm going to say EOK in this case, then we are happy to go through and actually toggle the LED and to print out some information and basically run the application the way that we're supposed to. Okay. And so we'll only run this if return value is actually okay. If it's not, what do we want? We don't want to return 0 and say, hey, everything is okay. We want to return whatever error code it is that generated a problem in the first place. Okay. And that could be no device from the pin not being ready, or it could be whatever the error is that's generated from the GPIO pin configure device tree function that's being called. Okay. And so right off the bat here, again, this simple Blinky LED application, which is just blinking an LED. We're going way too in depth about how we should actually structure this, but you can see that it's actually starting to become a lot cleaner, right? We're starting to actually understand what errors might be returned from this simple application, on top of being clear what state the LED is actually in, based on the pin state here. Okay. All right. So we've made some adjustments here. What else as we continue to read through this code? Well, I can see we got a return value from the GPIO pin toggle. We're making calls to the device tree, toggling the state of the LED. Okay, that's cool. We're directly adjusting the state of the LED. Here's a problem though. If we look at the rest of this code, the LED state here that we're storing, this code is in itself decoupled and disconnected from the toggling of the LED. That means that this LED state may not actually match the state that the GPIO pin toggle function is actually toggling. It could be actually turning the LED on, and we think that the state is off because we're just, even though we're toggling together, who knows what the initial conditions are for both of those, right? Hopefully we matched it, right, between the device tree and setting that the LED was off. And in this case, maybe I think we actually had true, which probably was that the LED was on. So we should make sure that we actually match those states, right? And you can see right there, very easy to get the states disconnected, right? And So, so again, real trivial example, but at the same time, you can see how we think through this. Okay, so another thing here, this if return value returns 0, again, we don't even need that anymore. We can actually save our application because what will happen is if we get an error from ret here, then we're going to end up exiting this while loop and returning whatever the error code actually is further up the stack. Okay, so again, real minor adjustment here, a little bit cleaner. Now, what I would actually do here in order to clean this up and connect LED state to the state that we're actually trying to toggle is I would actually take this code here. I would put it at the top here. Okay. So what we're doing here is we're saying, hey, I'm adjusting the current state of the LED to whatever it's going to be. And then what I want to do is I actually want to set the state of this. Now there's different device tree functions that we can use. Honestly, I would probably wrap all of this behind some type of LED interface. So I would have, an LED module that has LED init, LED, LED state set, and maybe LED toggle, right? And then behind the scenes there, behind that interface, that's where I would make the call to these device tree functions to be able to interact with the LED. Okay, so that right there is another thing that I would say is, well, not the greatest about the way the Blinky LED example is put together, but to keep things simple, we'll continue to kind of use the functions that they have here. Okay, so from here, I don't want to use the pin toggle. I actually want to use a pin set function. Okay, so there is actually GPIO set device tree, and it's going to take a reference or a point, the address of the LED, and then on top of this, we can specify whether we want it to be high or low. Okay, in this case, I'm going to pass the LED state. Now, I am using an enum here, so I am going to have to do something horrible and cast the state of the enum into a bool. All right. Again, not exactly, maybe not exactly the cleanest thing, having to actually perform a cast there. But again, we're taking an enum, which, is going to have a state there. And actually, we should look before I make that assumption. And again, this is where, let's see here. We want to look and see that it might not be that this is taking a bool. This might actually just take a, this might actually take just a value here. So let me take a look here if we can find the, I'll go to the Zephyr documentation here, and we'll make sure. Whoops, that's not what we want. Throw it in an AI browser, and it goes off into the weeds. So let's take a look at this particular. Oh, if I can find the documentation for it. Okay, so as it turns out, we don't have to perform this cast because it's just looking for an int. Okay, so the code stays clean, stays readable. We're in good shape. All right, and this is why we do code reviews and why we look at things and think through. Okay, wait, what's the type here that this is accepting? Again, these are all the types of things that you think through as you're actually writing and performing code reviews. And then this is kind of a review, but I'm actually making changes to the code live. In a code review, we normally wouldn't make those changes live. We just have a ton of suggestions, right? But I'm kind of allowing myself to make changes to the example on the fly here. So you're seeing this live. Okay, so with this change and the adjustment, I've got the LED state. I am now tying the pin state directly to this. And then you can see here that the LED state is being printed out over whatever USART or whatever console is set up in this particular application. I know it'll come out through a USART. So if we actually were to go and set up a terminal, we could actually see the printed state of the LED is on, the LED is off. Okay. From there, you can see here we've got KM sleep, which is going to run through and delay for that sleep time in milliseconds. for us, maybe we actually should have put, this doesn't specify how long of a delay. So maybe we actually want to say that this is, sleep time 1,000 milliseconds, so that it's actually specified, right? So that will clean that up so that if I'm reading through this code, I know that I'm sleeping for 1,000 milliseconds. Again, being clear and very intentional with what our code is reading. And so now if I look at this, I know that I'm changing the state of the LED. I am physically adjusting the pin state, okay? Now this could be an error that's returned, right? But assuming everything goes well, I print out what the current state of the LED is, which matches this state and also matches the state on the pin. Before, when LED was further down, it was possible that we were toggling and we were out of sync, or that things were being done kind of out of order. This way I actually have essentially a shadow variable that is dictating what the state of the pin is. And once I'm operating on the data, then I specify and move that data to the actual physical pin of my system. So in this way, I'm decoupling to some degree the state of the variable with the actual state of the pin, and I'm allowing the pin to reflect what is happening as part of my the data of my system here. Okay, so then we output and we sleep. Okay, if there is a problem, you might say, well, what happens if I change the state of the LED? I then try to set it on the pin, and I get an error. I'm going to print out the wrong state on the to the terminal, right? I'm going to say that the state is on perhaps, but maybe the GPIO pin errored, and then I'm going to delay it a second, and then what will happen is I'll discover that the return value is not okay, and then I'll actually exit and have a return code. Okay, so the only thing that will happen here is that it's possible that if I exit this particular thread, I might have a USART data that prints out the state of the LED as one thing, but it was never reflected on the actual physical pin. Now, is that a problem? I'm going to say in this case, no, it's not a problem. Not just because it's a blinky LED, but because we actually exit the thread here and return a code saying that there is a problem. And so I could look at my log, I would see that the state was set, and then I would see that I exited this thread, and I could check the return value to see that, oh, there's an error that was produced by the pin set device tree. And that would very quickly guide me to the point that there's something going on there, maybe with the way my device tree is configured, or based on whatever that error code happens to be. All right. So at this point, this is just an example of a simple walkthrough of a blinky LED application, something that should be pretty simple. And I think what you probably have seen here is that even a simple LED blinky, there are little tweaks and adjustments that we can make to this code to make it a lot clearer, a lot cleaner, and to help us understand what exactly the intent of the code is. Now, again, this is just a simple LED blinky. You can imagine if you're working on some type of low power energy converter, or you're working on some type of controller, or doing motor, maybe doing motor control or propulsion control, or whatever it happens to be. Having the code much cleaner and clearer won't just help you to eliminate bugs. It will help prevent new bugs from being injected into your code. It'll make it so that when you pass this off to the next developer, they can read this code and very cleanly understand what the intent of your code is, and overall make it so that you don't have a whole bunch of technical debt sitting there preventing you from getting real work done. Okay, and to be completely honest, writing this code like this in the first place, it didn't have to take probably what are we talking about here? Probably 20 minutes, 20 or 30 minutes to go through and do this code review. It did not need to take this long. If I were to actually go through and do this myself without explaining what I'm doing and why I was doing it, it would probably take me about 5 minutes. Okay, but hopefully that gave you some insights into how you can think through code reviews, but also when you're writing your own code, the types of things you should be thinking about as you write that code. So with that in mind, I hope you found this interesting. Happy coding, and I look forward to talking with you again in the future.